Welcome to the webinar All-in-One Electron Microscope. This webinar is co-hosted by Media System Lab and Delong Instruments. We are introducing the innovating and amazing electron microscope LVEM25E. Let's start with the company presentations. Media System Lab first and then Delong Instruments. Enjoy the webinar. Hello, my name is Matteo Mariani and I want to introduce you my company Media System Lab. We are a growing family company with 25 years of experience in electron microscopy. Our common value is to pursue quality in everything we do in our daily job, in support and service, and you can see also today in products and partners. We have mainly 4 departments: electron microscopy, sample preparation, support and service, and our portfolio for the life sciences is called MS Biolab. In electron microscopy, we can provide tools like the Delong instrument Compact TEM, LVEM25E, we are introducing in the webinar today, SEM's compact and traditional ones made by Coxem, and for those microscopists with known standard needs, we are able to provide our custom solutions for SEMs. For the life sciences, in our portfolio MS Biolab, we have the live cell imaging microscope from Nanolive, the 2 photons microscopes from Photonics, and the laser-free confocal microscope by Aurochs. Media System Lab has been built on competencies, and you can taste our competencies and experience in electron microscopy service, in application support, and in training. We provide training on customer sites and by remote online through our platform called MS Academy Lab. For sample preparation, we can provide anything you will need in your lab, from cutting, polishing, sputtering, IO milling, plasma cleaning. Just ask, we have anything you will need. As I said, it was a brief introduction. Thank you very much. You can meet us in person in Macherio and Rovereto in our 2 facilities in Italy, or online on LinkedIn, Twitter, and Instagram. Thank you very much. Today we will speak about the low voltage electron microscopes. Our colleagues from Delong Instruments prepared a short introduction to the company and the instruments. Please enjoy.
Greetings from Brno, the world center of electron microscopy. Today we will speak about the newest all-in-one electron microscope, but before we start, let me briefly introduce our company and the concept of low-voltage electron microscopes. First, let me introduce our company in a short video. For over 30 years, we have used our experience to support our customers worldwide by providing solutions in 3 divisions. Most of the time, our core business was custom solutions, including R&D services, specialized components production, or OEM solutions from the first draft up to the repeated production, mainly electron-optical devices, but also projects outside the field of electron optics, such as optomechanical manipulators for the world's most intense laser system. Nevertheless, most of our custom solutions are in strict NDA regime, letting us only disclose that we also provide many other interesting products. First of our branded product lines are the guns. Delong instruments low-voltage Schottky electron guns that serve industrial purposes or as Lego bricks for scientists who want to build their own systems. The low-voltage electron microscopes used to be a fringe product line. Several years ago, we decided to make them Delong Instruments' flagship and started promoting them. LVEMs are absolutely unique. The concept of small and powerful transmission electron microscopes, a direct inheritance of Professor Delong, our long-term colleague, is based on his vision that transmission electron microscope should be something like personal computer for scientists, always on hand. And that's why our TEMs are small and undemanding, to be installed easily in any lab and operated daily for a reasonable cost. Small and portable, we can bring LVEMs anywhere to introduce them better than in any presentation, as, for example, to Rome this June. Professor Delong was a great teacher, and his electron microscopes, robust and easy to use, are great for students from undergraduates to PhDs, as first electron microscopes in the lab, or for training users before proceeding to big and expensive instruments. Such trained users, with their routine tasks, can also be redirected to work on an LVM alone. This can reduce waiting times for big TEM and increase the efficiency of the shared lab. Also, the efficiency of research teams with a high throughput of samples, such as chemistry, biochemistry, or nanomaterials, can be significantly increased by employing a small device directly in their lab. Low voltage means a naturally high contrast that helps LVM users to reduce staining, whether for diagnostic or scientific reasons, especially when the layers of stain hide essential details of the sample, or just to reduce time and money, as well as the health risks and environmental load connected with staining. Another advantage our customers appreciate at LVMs is universality. And here comes the new LVEM25E, pushing the limits of universality further, by offering a unique option to obtain multiple data results from one sample by switching between the imaging modes using intuitive software. The LVEM25E shares several key concepts with the other LVMs and brings several improvements, especially higher automation and further analytical methods. LVEM25E, running on 25 kV, is, like all LVMs, basically a transmission electron microscope with electron diffraction connected with the TEM in the basic setup. The optional 10 and 15 kV STM mode provides even higher contrast levels and allows for analyzing of thicker samples. SCM mode option offers backscattered electron analysis of sample surfaces. And the long-demanded optional EDS mode further increases the application of LVEM25E by adding the sample's chemical composition analysis and creating element composition maps which can be overlaid with the STM and SCM data. For users in materials science, LVEM25E provides the possibility to measure internal and external structures and analyze the chemical composition of the sample, all in a single device. In life science, The LVM25's users appreciate especially the well-contrasted and highly detailed images from samples prepared with standard preparation protocols and the option to obtain the same level of detail with reduced staining. Nowadays, we can see the borderline between material and life science vanishing, opening a new space especially interesting for the correlation of several analytical methods on one sample. LVM25E can provide such correlation during one imaging session, as in this case of zebrafish pancreatic cells with golden immunolabeling concentrated in insulin. So, during one imaging session, we can easily get a quick sample overview in TEM and quickly find the point of interest. Improve the contrast and resolution of this thicker sample in STM. Check the metallic character of nanoparticles in SEM with backscattered electrons. And verify in EDS that the metal is gold and that the gold is bound to insulin, which has a high share of sulfur. And we can also add electron diffraction, all from one sample, one device, and one time slot of about 1 hour. Well, that's all from me for this moment. Now, let me hand over to Product Manager Eva Zoufalova to introduce the LVM25E to you.
The LVEM25E is a compact transmission electron microscope working at 25 kV. In the basic setup, it is an easy-to-use device for imaging standardly prepared life science samples. In the full setup, we call it all-in-one electron microscope because it enables the user to analyze the sample in several different ways. In transmission and scanning transmission mode for ultrastructure, electron diffraction for crystal structures, scanning electron microscope with backscattered electron detector for outer structures, and EDS for chemical composition. The microscope has a very small footprint, needs only one plug to be connected to the mains, no water cooling, no special gases or compressed air, and is even portable. That all with a resolution better than 1 nanometer and naturally high contrast that enables staining reduction or replacing traditional stains by new non-toxic ones. Now you can see the working place. The system is upside down with a FEC Schottky cathode with high coherency, brightness and lifetime placed on the bottom of the column. The sample holder is inserted here and an automatic airlock valve enables a wizard-supported sample exchange. The airlock is quickly pumped by a turbomolecular pump. Pumping of the whole system provided by ion getter pumps means a clean and high vacuum preventing sample contamination. The image is captured by a 4.2 megapixel scientific CMOS camera. For EDS, we use a solution by Bruker.
Now is the time to dig into the applications of this amazing LVEM25E. We need Jaromir Bakowski, application specialist in Delong instruments, to tell us more about the TEM, STM, EDS, SEM and electron diffraction modes of the LVEM25E.
Good afternoon, ladies and gentlemen. Thank you, Matteo, for introducing me. It's a great pleasure to have an opportunity to tell you some information about the applications of LVEM25E, the new generation of low-voltage transmission electron microscope. If I would try to find one appropriate word to describe the whole instrument, I would probably choose versatility, because as you will see, the possibilities of this device are enormous. This electron microscope is referred to as an all-in-one microscope. It's not just because the column and all electronics are placed in one single case, but also because it can be equipped with all main microscopic modes. Thus, the application areas of these microscopes are extremely wide, and it's a very powerful and versatile device. The first question which should be answered is why should you prefer low voltage transmission microscope against the conventional ones? The most important advantage of our system is extraordinary image contrast. The lack of contrast is a well-known phenomenon in the case of transmission electron microscopy, but our low-voltage devices can provide great image contrast, even for the samples consisting of light elements, typically biological sections, where, for example, different organelles or membranes can be resolved with unprecedented contrast. The explanation for this property can be found directly in physics, since slow electrons are much more scattered than fast ones, which pass almost unnoticed by the sample. On the contrary, the slow ones have much more time to collect the information from the sample. A direct consequence of this property is that we can reduce or even eliminate the staining, and even without staining, we reach comparable results as in the case of conventional instruments with stained samples. And we all know that staining agents are not so pleasant substances, so it would be great if we can at least reduce their dose or even avoid their usage completely. We can prove the extraordinary image contrast on the cyanobacteria. The unstained samples was studied by the conventional TEM and then by LVEM25E. I think that the results speak for themselves. However, I will not get ahead of myself because you will learn about this study from its main author, Katka Mrazova, later during this webinar. LVEM25E is a dedicated TEM with resolution 1 nanometer, but it can offer much more. Every single optional mode significantly expands the application range. TEM itself is especially convenient for routine imaging because it's very fast and robust with respect to vibrations. I prepared a collection of interesting pictures through various life science applications. So, TEM finds application mainly in the field of pathology and histology. Currently, very interesting are the applications in virology or other microbiology, where you can benefit from a fast and easy routine operation and amazing image contrast. The application area of TEM mode in life science is not just biological sections, but LVEM25E is often used also in pharmacology or biochemistry to investigate, for example, nanoparticles. But also purely material science sample can be investigated, such as polymers, crystals, or morphology of quantum dots. We highly recommend our customers add the optional STM mode. Actually, there are two of them. It's available for 15 and for 10 kV. The resolution is very close to the 1 nanometer for both of them. STM imaging properties will especially appreciate the customers from life science who want to work with thicker sections, because scanning transmission is not sensitive to the additional broadening of energy spectra by the sample itself, and thus it deals better with chromatic aberration. Here is an example of very thick sections of about 200 nanometers, which can serve as a proof of STM capability to handle blurred TM images caused by the interaction of the electron beam with the sample. But SEM provides very nice images also for material science, especially in the case of light elements, and you can also use the both imaging modes, dark field and bright field. For material sciences, we can also emphasize electron diffraction, which can be used to assume crystallographic structure. The very typical of electron diffraction is graphene, which can benefit from low energy not only during imaging but also in diffraction regimes. But electron diffraction is not only a matter of material science samples. It can be used also for an organic component of life science samples. A very nice example is a study of calcifications, which can be a symptom of pathological changes in soft tissues. Prove the capabilities of LVEM25E in this application area on diffractograph of compact bone or shell clamp. The aforementioned modes are nothing new, and they were available also on all the generation of LVM25. Although there are some major improvements, but I will focus on functions added on the novel instrument. The most significant innovations that we added are an SEM detector for surface investigation of bulk material and an energy dispersive spectroscopy for chemical analysis. Let's start with SEM. The unique combination of transmission modes and SEM is so popular with customers of LVM5, smaller brother of LVM25E, that we decided to equip the new generation of LVM25 also by the SEM mode with the detection of backscattered electrons. It allows us not only the investigation of diverse non-transparent bulk samples, but we can also use SEM for imaging of thin sections, which provides us with another dimension of imaging possibility. The majority of the signal in this case comes from the stained parts of the section or other parts made of heavier elements, so the information is complementary to the information obtained from transmission modes, and you can easily correlate between these two kinds of contrast mechanisms. Although LVM25E is not a dedicated SEM device, it's still a very powerful tool with the resolution of approximately 3 nanometers. There is only one disadvantage. The device uses an inland system of TEM optics, so the sample is loaded between the pole pieces, and there is not unlimited space between them. Thus, the sample has to be comparable in size with TEM grid. Of course, there can be a discussion if it's enough or not, but considering that LVM25E is a microscope, which is usually used for imaging of very small objects, so there is still plenty of space on the stump, where we can place an incredibly rich portfolio of the possible samples from insect to crystals. The second added mode is concerning to the chemical elemental analysis to make LVM25E even more versatile analytical tool. We implemented Bruker EDS system. Users can benefit from the spectroscopy in TEM mode with energy of the primary being 25 keV, kiloelectron volts, but even more cool is EDS in scanning regime. both STEM and also SEM, where you can do elemental mapping and get information about where individual elements occur in the sample. For easy evaluation of spectra, you will use user-friendly and very sophisticated Esprit software with almost endless possibilities how to process your measurement. You measure integral spectra from whole scanned area, do the mapping, do the selective area mapping on the arbitrary part of the image, or even extract the spectra from the single point of mapped area. And of course, correlate all of this information with the image provided by STM. As an example, I picked here the sample of nanoparticles composed from silica, titan, and silver, where the mapping feature is nicely shown. So, it was a brief introduction to the main applications of LVEM25E. Because I'm already short of time, so I have to say thank you for your attention, and in the case of any question, do not hesitate to contact us. We are ready to answer them. Thank you.
Thank you very much, Jarek. It was amazing. Can you show us now how to use the LVEM25E?
Okay, so I will show you the typical workflow on LVEM25E, and I will briefly introduce the operation with all important modes. So when you come in the morning, you start the emission. It's great that you don't need to spend your time with whole alignment procedure, and you can immediately start working. So first of all, when you load the sample after the start of the emission, you usually go to the low Mach regime to screen the whole sample and find the important parts. So it takes some time to set all important parameters, and here we are. We set the exposure time of the camera, and we can see approximately quarter of TEM grid, and we can easily find interesting places. We can store the places on the specimen window. And when we are fine, we can go back to TEM. Set again some exposure times and setting of the camera. We use the appropriate apertures, and we can immediately start imaging. So we can choose appropriate magnification. Of course, we have to focus. There are very cool features, auto beam alignment, which let's say stay with the beam in the center of the field of view. We can also improve the image with summing, find the specific place, and focus on that space. For focusing, we use movement in the Z position, and there is a very great feature which is called autofocus. When we say to the microscope, okay, this image I like, this is focused for me, so I click on the set as focused, and after that, if I change the magnification or illumination, the microscope stays in the focused state. We can also improve the final image with histogram. course, it depends what you like, what kind of details you want to focus on or emphasize. And of course, we can also measure some interesting parts, for example here lipid droplets, and do some basic statistics from the data. Okay, so I clear it. We can also draw some other patterns or combine them. We can also measure some areas and so on. Okay, we will increase the magnification a little bit to focus on this nice mitochondria, and we can try also scanning transmission mode on this specific place. We have to turn on the photomultiplier because in the beginning it's turned off due to the security reasons. Now we have to focus. So image is almost focused, at least what I can recognize in this magnification, and I have to play a little bit with the contrast and brightness. It again depends what you like to emphasize, what kind of details. And now we can change the magnification by simple clicking on the zoom scale. And if we want to use the fine focus function, we can choose some specific part of the sample for faster scanning and focus it more precisely. Okay, and here I skipped to EDS. We activated this, the scanning from Bruker system and move to the Bruker software called Esprit. You can see that the operation is very simple, and I can immediately start acquire the image, and then I can start with the spectroscopy. The auto ID function, let's say, identify the most probable elements in the sample, but you can check it in spectra and find let's say the elements which are present in the sample, and you can do the mapping, of course. So in the quantitative EDS, you can let's say fit the spectra with the elements which are present. And now I switch to BSC detection. Of course, not all of the samples are let's say interesting in all modes, but sections can be observed in SEM, so we try it. The operation is very similar to scanning transmission, so again I had to let's say increase the contrast. There is a zoom scale for changing the magnification and of course brightness. I have to focus image again, and here we have the image in the inverse colors. Okay, so it was very brief introduction for modes of LVEM25E. For the more detailed specifications and operation, we are here for your question. So thank you very much.
Great, thank you again. Now we have the chance to appreciate the user's experience of the LVEM25E. We have now a presentation made by Katerina Mrazova, a young scientist from the Institute of Scientific Instruments of the Czech Academy of Sciences. She's going to tell us about her work made with the LVEM25E. Indeed, she focused on reducing toxic materials from the sample preparation process.
Good afternoon, ladies and gentlemen. I would like to thank the Delong Instruments for the possibility to share our work today with you here on this webinar. In my presentation, I would like to share with you the results of our study dealing with the employment of low-voltage electron microscopy for the study of cyanobacterial cells. The first question to be answered is, why to use low voltages in transmission electron microscopy? As we are all familiar, when imaging biological samples using conventional high-voltage TEM, it is necessary to stain the sample using most commonly uranyl acetate and lead citrate. However, both of these substances are highly toxic and need special disposal. Also, recently legal restrictions concerning handling and disposal of uranyl acetate call for the different solutions. There are already studies dealing with the novel staining agents. However, if we take the advantage of imaging techniques using low-energy electrons, we can avoid the staining procedure and still get sufficient signal even from the carbon-based method. Our model organism of choice was Cyanobacterium Synechocystis PCC 6803. It's a unicellular microorganism with well-described intracellular structures. It can also produce biotechnologically interesting biopolymers, such as polyhydroxyalkanoids. The presence of polyhydroxyalkanoids in the cells enhances the robustness of the cells, and also, from a microscopic point of view, polyhydroxyalkanoids have also interesting properties, such as they stay elastic even in the temperatures of liquid nitrogen. Then they can be seen sticking out of the freeze-fractured cells as seen on the image on the bottom. So, for the experiment, the cells were fixed using the high-pressure freezing method, followed by freeze substitution in the solution of 1.5% of osmium tetroxide in acetone. Samples embedded in EPON resin were then sectioned and either left unstained or stained using uranyl acetate and lead citrate. Sections were then imaged using three types of microscopes: high-voltage TEM Talos F200C, low-voltage TEM with stem mode LVEM25, and SEM Helios G4 equipped with stem detector. For the TEM imaging, we studied both stained and unstained samples using either 200 kV or 25 kV electron beam. As expected, stained samples imaged using 200 kV provided us with nice contrast and resolution. However, samples stained only by osmium tetroxide in freeze substitution medium were almost invisible, and some of the structures seen in the stained samples are indistinguishable. Nevertheless, the unstained samples imaged by 25 kV beam gave us sufficient contrast and quite comparable with stained samples imaged by high voltage transmission electron microscope. Unfortunately, stained samples imaged by 25 kV were in some cases, on the contrary, too dark to recognize all of the structures in the cells. Also, it is possible to see that both images acquired by LVEM25 are not as sharp as the high voltage image because of the chromatic aberration occurring when imaging thicker samples by low-energy electrons. This issue, however, can be overcome when switching to STEM mode. As you can see, both of the images acquired by LVEM25 are sharp and provide nice contrast. The benefits of low-voltage electron microscopy were also confirmed by imaging the samples in SEM Helios, which is equipped with the STEM detector. So, to sum up, we are all aware of the benefits of imaging of biological samples in high-voltage transmission electron microscopy. Unfortunately, the usage of staining agents require careful handling, and also there can be a source of contamination. The low-voltage transmission electron microscopy can avoid the staining procedure itself, making the procedures faster, safer, and cheaper. While the problem with the chromatic aberration can be solved by switching to the STEM mode imaging. So, with this, I would like to thank you for your attention.
Thank you very much, Katerina. It was a great presentation, and congratulations to you for your just published paper. You can find it on the Delong Instruments website. Thank you very much to be here with us and to join the webinar. Please visit the Delong Instruments website, the Media System Lab website, and join also our platform MS Academy Lab. See you in the next webinar.